today I'm going to talk about artificial intelligence. More specifically, the Trinity of AI. What are the three main ingredients that make AI happen? And what's the fabulous future we are headed when it comes to AI? And I'll combine both the academic perspective I have from Caltech as well as the industry perspective from NVIDIA to see how there are so many exciting opportunities for industry academic collaborations to come together and realize the dream of AI. But before we get there, what is AI? Right? I'm sure everybody here in the audience has seen AI in the news, has seen both, amazing progress that AI has done, but also some dystopian future for AI that people are worried about. But given that it's so much in the news, the first question we should be asking is, what is intelligence? Before we get to artificial intelligence, what do we even mean by intelligence? Right? So for this, I want to show you two videos, and I want you to think which one of the two is more intelligent. So let's see that. So the first one you see is the Boston Dynamics Atlas robot, right? That's a pretty cool backflip. Now, what about the next one? So again, it's our best friend. It's also trying to do a backflip. So in the first case, you see the robot perfectly executing the backflip. In the second case, you see it failing pretty clumsily. So what do you think is more intelligent, the robot or the dog? Yeah, it's the dog that's intelligent, and the robot actually has zero intelligence the way we have it today. So why is that? Because how do we define intelligence? The intelligence is the ability to acquire and apply knowledge and skills, right? Was the robot doing that? No, right? At least the way it is currently, it was completely pre-programmed. Even though the backflip looks so impressive, it was all planned beforehand, and the program was built into the robot. On the other hand, the dog is improvising. It's always observing its environment. Maybe one day it'll also learn to do the backflip better. And so the dog is intelligent, while our current robots are mostly not. And so there you see a very big gap of where we are when it comes to building intelligence into our robots, into our systems. And indeed, when we think about general intelligence, the gap is even wider. So general intelligence refers to having human-level cognitive ability. And artificial systems are so far from it. So when I refer to AI or artificial intelligence, I usually mean some task-oriented intelligence. It's the ability to execute a specific task very well, right? To learn from examples and to execute a given task. And that's what I'll show you how we are making progress on, and still the vast challenges that lie ahead. So given that we got the definitions out of the way, let's now see what is the Trinity of AI. So for AI to be successful, I see three important ingredients. The very first one, and perhaps the most important one, is the data. Right? So when I say data, I mean examples. Like how can a system learn? It needs information, observations, or data. And so once it has it, there are learning algorithms which can process the data and extract knowledge from those examples. But the third important ingredient is the compute infrastructure. All this processing needs a substrate. How do we do this vast amounts of processing? So we need all these three to come together for an AI task to be successful. Let's now see an example application and see how the progress came about by putting this trinity together. So the image classification task has been perhaps the most visible success of AI today. As you see here in the picture, there is the pool, there are plants, so there's a lot of things in this image. And as human beings, we find it so natural to absorb and reason about the entire image, right? But it's really hard for a machine to do that, because it has to see lots of variations of a swimming pool before it realizes, oh, this is a swimming pool, right? So it needs a lot of examples to learn what a swimming pool looks like. And that's where we have the first ingredient in our Trinity, that is the data. How do we get lots of examples of images for different categories? So the ImageNet dataset has revolutionized how we've done computer vision. And that's because for the first time, we had such a large collection of categorized images. This is more than 14 million images and more than 1,000 categories. And if you even look at one example category here, you see all the variations of how natural images come about. For instance, when you say fish, you just see so many different variations of how a fish can occur in an image. And so the learning algorithm needs to have access to all these different variations for it to recognize what a fish looks like in a new example. So that was the first ingredient, the data. The second ingredient are the algorithms and the models. How do we take these images and extract the information so that an AI system can automatically categorize images in a seamless way? And that's where we have the deep learning models. So the term deep refers to the fact that there are many layers of processing. So you transform your input image across these layers, and in the output, you want an answer. You want to say, with how much confidence do you think there is a dog in this image? And if you have a good algorithm and you've trained your system well, hopefully you will have a high confidence that this particular image has a dog in it, right? And so you need a model that's highly flexible, that can learn from millions of examples and extract the relevant information to realize what looks like a dog. So those were the two ingredients. The third one is the compute infrastructure. So if you take these current deep learning systems, it is just not scalable to run it on a normal computer. So the computers of yesteryears, or the CPUs, had a wave of progress, but now the curve of their growth is plateauing. And so the new form of computing is known as the GPU computing. It stands for graphics processing unit because it goes back to how graphics was processed in a parallel manner. But the same form of technology is also highly relevant for processing AI, because processing in these deep learning layers requires more than 1 billion operations for each image. But they can be done in a highly parallel manner, and hence NVIDIA GPUs have been at the forefront of enabling computation at scale and have been a crucial ingredient to realize this dream of large-scale AI. So now you see how all these three ingredients came together. So we had the data, we have the deep learning model with learning algorithms, and then we had the GPU computing. And when they came together, it created this deep learning revolution. We were able to make progress in such a short length of time. So what you see is the error that an AI system makes in recognizing the image, what are the categories in an image, over this ImageNet dataset. And you see, within a span of few years, we could get to human-level capability on this dataset. And so to have this capability on such a large dataset in such a short amount of time was what was surprising to so many scientists. And so that shows that there is a lot of promise that AI can still realize in many other domains. I do want to point out one thing, though. If you see, in 2015, on the ImageNet dataset, the AI system is doing better than a human being. So does this mean the AI system got more intelligent than a human? No, that's not the case, right? Because it's only doing better on only this data set. And that's always been a challenge with AI if you have to now take it beyond to other data sets or to other tasks. So we need the ability to generalize beyond what it's seen in a current data. And that still remains in this case as well. So that is great. We were able to make fast progress, but where do we go next? So my research looks at how to do learning in many dimensions. So what do dimensions mean for data? So if you think of an image, you have the width and the height of an image. And then if it's a colored image, you have the number of channels. Now, if you take a video, you also have the time dimension. So when you collect rich forms of data, you have many dimensions coming together. For instance, you may also have text that is connected to the video. You may have other forms of data that are all processed together. So how do we merge all this very efficiently and process them at scale? So the idea is we don't want to remove or throw away the dimensions in our data. If we do that, we can potentially lose information. To help you visualize this, you have the three-dimensional cube here. And if you just look at its projection on the wall, you do not see the complete picture, right? And it's the same with data. If you're not processing it effectively and not incorporating the information from all different dimensions, you may potentially not learn very well. What my research does is to use mathematical objects known as tensors to enable such multidimensional processing. So tensors are mathematical objects that do processing in any dimension and generalize the concept of vectors and matrices that you probably see in an undergraduate class. So these may seem like complicated mathematical objects, but you can realize them into real algorithms for many applications. So one application I've looked at is how to automatically categorize text documents. So if you have millions of documents, can you quickly say, what are the topics discussed in various documents? Right? And if you don't even know what the underlying topics are, you don't have examples of them when you're learning, it's even a harder task. But we have a tool that I built with my team at Amazon called Amazon Comprehend that precisely does this. And what enabled this algorithm was the concept of tensors. So intuitively, what it's looking at are the relationships of words in a document. So if there are words that are commonly occurring together that refer to a topic, you should be able to extract that information. And to do that at scale over millions of documents requires more thinking, but that's precisely what these algorithms are able to do. They can take this co-occurrence tensor of triplets of words and decompose them to obtain topics that are present in different documents. And hence, you can translate mathematical concepts into actual algorithms and then deploy them at scale to make an impact on various applications. So I see a lot of possibilities in future to take this multidimensional processing into many different applications. So what's another step for the future? So I want to think about both the mind and the body. So far, I only talked about AI as the mind, right? How do we create intelligence? How do we train an AI system? But there's also the body, which is the robotics. So I showed you in the beginning the Atlas robot that currently is not intelligent. If we want to change that, we have to bring the two together. And at Caltech, we have the Center for Autonomous Systems and Technology that aims to do that. So I'll show you one example we just started working on, which was to ask, can we have the drones learn to land better? So instead of a pre-programmed algorithm, can the drone learn from lots of data, lots of sensors that it's outfitted with, and be learning to land in a better way? So let's see what was the outcome. So on the left, you see the drone when there is no learning. It's a programmed controller. And in the right, there is the learning. And if you see on the right, the drone landed, whereas it was hovering around in a pre-programmed controller. So this means there is a lot of potential that learning can provide to make drone flights more efficient and ultimately autonomous. Another project we are currently thinking of is how can we have drones fly in adverse conditions. And here we can simulate wind conditions of all different forms in the drone testing laboratory at Caltech, and then you collect that data to design AI algorithms that can be more effective in countering such wind conditions. If you want to bring the mind and the body together, you want to build all different forms of intelligence and meld them together with the body. So we want the robots of our future to be instinctive, right? So humans have instinct inbuilt in us, which is the ability to react and control our reactions in a fine-grained manner. How do we do that in a robot? We're also deliberative. We make plans. We look at consequences. How do we do that in a robot? It's also multi-agent. We are a society. We coordinate and work together with others. How do we get the robots to do the same? And ultimately, the last one, perhaps the most difficult one, is behavioral. How can we have robots that can interact with us, that can understand human emotions, ultimately be a partner with us? And that's perhaps going to be a bright new future for us. Thanks so much.